So let me introduce the speaker. So today it's a great fortune to have Dan. He's a researcher in software engineering from NVIDIA. So he get his PhD from University of Chicago, and we both interned at JP Chase summer 2023, and since then I know he's an expert on tensor-network method, and I think today he's going to talk about those methods, also something related to quantum error correction, especially decoding error syndromes. So I will let the speaker take in charge. Dan, you can go ahead, and you will be in charge now.
Thanks for the intro. I need permission to share.
My bad. Let me do that. Let me fix it. Yeah. Yeah. Can you try it again?
Yep, this works.
Great.
Okay. So this talk is going to be about a particular algorithm called belief propagation, and it has surprisingly many applications. One of them is error correction. I will talk about 3 applications actually, and this is the outline. I'll start with describing the message passing and then continue to belief propagation algorithm. And this part will probably be relatively easy, pretty much no prior knowledge required. But for the application, it did turn out to be pretty condensed. So this is for people who already have some familiarity with error correction or tensor-network simulation. I'll try to explain as best as I can, but this is more of a pointer to where you can go look into, like if it catches your interest, rather than explaining it fully. So with that, let's start. So I'll talk about message passing first. Message passing is an algorithm how to calculate some, in general, some global property from local rules. So imagine you have a chain of soldiers that are going somewhere in a field, in a foggy field, and you can only see, you as each individual soldier, you can only see the person, or see or hear the person in front of you, or one person in back of you. And you want to calculate the total number of soldiers, and how would you do that? You can't run and count everybody by hand because it's very long distance. So you, as let's say, as a leader, you establish a rule that says, okay, now each soldier listen for a message that comes to them, and then pass that message to the person of either in front of you or back from you. So if you hear from front a number, you add 1 to it, and then you pass to the back. Okay, it's pretty simple local rule. But if you run it as a leader, so you send the message backwards, 0, and you send the message forwards, another 0, and then you wait for the messages to return. What you will end up getting is number of people that are in front of you, a number of people that are from the back, and you just add those 2 numbers, you add yourself, and you get the total number of people in your line. Pretty simple. And just based on this idea, we can build on top of that and apply that to more complicated scenarios. So let's say we now have, instead of a chain, we have soldiers kind of scattered around, and you can only kind of communicate with your nearest neighbor. And let's say you can form a tree, a graph of communication can be represented as a tree. Now we can apply the same approach. You receive all the messages from the leaves of those trees, and you add 1 to those messages, to the sum of those messages, and you pass the message to a person that you didn't receive the message from. So the rule is, if you have number of neighbors, if your number of neighbors is n, and if you received n minus 1 messages, you pass the value that you received so far. So conceptually, I like to think about this like you have two parts. You have like the here part, and you have their part. So you subdivide the parts that the messages that you receive. You kind of, okay, here the number on the one side, on my side, is this, and you pass it to the down the line, down the chain, there for them to receive and further process that information. So the forward rule is that if you receive the n minus 1 messages, you pass the value that you received from your value that you received so far. And then there's also the backward rule, similarly to what we had in the chain. Once you received all the messages, then broadcast the received message to everyone else. So this is for the commander to receive the backward. So in this case, the commander can be anywhere. The commander can be like down here, and he will still once all the messages arrive to some soldier, they will broadcast back, and then it will trickle down to the commander, and he will receive the number of all soldiers. So the forward rule that we have is at the top, and then the backward rule is that once you receive the message where you received, so once you receive the message from there, you broadcast the values back. Okay. And by the way, feel free to interrupt and raise questions. This is like a introductory part, so it's pretty good if everybody gets what I'm talking about. So let's kind of walk through the algorithm first. We start with the leaves, and then for them, the number of neighbors is 1, so therefore they have to start, and then they received n minus 1, which is 0, so they are starting with the forward rule. They send the messages to this guy, this, and then once the forward rule finished, the person who received the amount of messages that equals to number of neighbors already has all the information, and now he can start back propagating that message to everybody else. So this would work, but crucial thing about this algorithm, and this is also a property of belief propagation in general, if you have loops, what you end up doing is you end up just infinitely looping and passing the messages around. So you will essentially never end. So this will break pretty easily if you don't have this loop property, and you have to treat it especially. So I'll talk about it later. And so applications for message passing are a very wide range of applications. So error decoding, I will talk about it, about the error decoding. There is an algorithm for pathfinding. You can think about message passing as a thing that you do in dynamic programming, where you have the leaves as your edge cases, and then you pass the message upwards to the chain. So it's a pretty wide concept. And then we can apply belief propagation. We can apply message passing to calculate some particular values on a thing called probabilistic graphical models. And that application is I'm actually not sure if it's the definition. I don't know if there is one definition of belief propagation, but at least this is how I learned about it, about belief propagation. So let me introduce what is a probabilistic graphical network, graphical model. It's intuitively a simple concept where you have some set of probabilistic variables, such as you could have a variable called difficulty of a class, and there is a probability that the class was difficult and not so difficult. So difficult would be D1, and the probability is 40%, and difficulty of the class being not difficult is 60%. And then you can have a variable called student intelligence. You don't know the student, so you have either the student is very intelligent or not so intelligent. You can have some prior knowledge about that as well. And then you can model other variables using these inputs. So you can model the grade. For example, you can say that for low intelligence and low difficulty, these are the probabilities that the student will receive such and such grade. Let's say we have 3 grades, 1, 2, and 3. And you can see that, for example, if we have a difficult class and low intelligence, we get a high probability of getting grade 0.7, so which is like a bad grade. Or if we have high intelligence and easy class, we get high probability of getting grade 1. And then you can also correlate that to, for example, SAT score. So the probabilistic graphical model essentially is a way to model a very high dimensional probability distribution. So the probability distribution that you would write for this network, it would involve 5 variables. So you would need to kind of list out every possible combination. But it turns out that in some cases you can factor out that cumulative probability distribution into these pieces, and there is also a causality element here. So this particular case is called Bayesian network. There is also an undirected version called Markov random fields. I won't talk about that, but it's a very similar concept in it, but you don't have this kind of causality. It is also very similar in a sense that you are able to represent things that are factorized in your probability distribution. And this internally is linked to the notion of independence of variables given other variables. So for example, difficulty and intelligence are independent. So it doesn't really make sense to have them enter your probability distribution as if they are dependent. Okay, so belief propagation is an algorithm that allows you to calculate probabilities, marginal probabilities. So in the case of, actually, gosh, in the case of the student network, you want to calculate the probability of a letter given that you have probability of difficulty and intelligence. That is called a marginal probability. So you want to sum over all the other variables and get a marginal probability that a letter will be this or that. So the way you do this is you can apply belief propagation for that. And again, you can create from this Bayesian network, you can create a thing called a factor graph, which essentially represents each conditional probability as this square. So the variables, they are still the circles, but now each square represents the data that we have. So for example, initial probabilities of difficulty and intelligence, they are encoded as these squares, and we could have this square that encodes the conditional probability, like in the previous example. So after you, this factor graph is a very similar thing to a thing called tensor-network. It's in fact the same thing. So there is a deeper connection between the factor graphs and tensor networks and quantum circuit simulation, which like they're talking about the same thing when they talk about the factor graph and tensor networks. And now again, the main task is compute the marginal, which is represented as a summation over all the variables that you don't care about. You want to get a value, the probability for values for the final, the marginal. So we could say that our probability distribution for each case is represented as this factorized as this. This is just writing down using math some structure, and so here I just show an example of the Markov random field, so not directed graphical model, and this one can represent some kind of image processing situation where you have input nodes that are black circles, and then you want to reconstruct information about what is located in this or that pixel. So you can have a conditional probability. Okay, this is a dog or a cat on that pixel, and that could be encoded in these conditional probabilities that are essentially within the edge. So again, converting to the factor graph would give you this kind of notation where each edge corresponds to this factor in the formula. And as a side note, this one actually has a very tight connection to physics. If, for example, you can encode the energy of the Ising model, or more general Potts model, in the same way. So this probability distribution that I have here, it can represent the same thing as the energy, and in fact, if you define the energy as such, you would get the probability distribution that can be represented, that can be factorized as this. So there is a pretty deep connection between calculation of the free energy of a physics model and belief propagation. So this is kind of related to the recent Nobel Prize, actually, because Nobel Prize was given for studying these kinds of model, not the Potts model, but a very similar, like a spin glass model. It would have a different structure, but it's very similar. So this kind of a motivation. They give Nobel Prizes for this. Not for this in particular, but related research. Now let's go through the belief propagation. Like what does actually do? We have some nodes and we have some edges. Again, we can think about the edges as tensors, or like it's these factors that connect the edges. And we want to calculate. So I'll just define the algorithm and then just kind of postulate that it gives you what you want. And we start by initializing a set of messages from each node to another node, and forward messages and backward messages. And let's say we want to initialize them to 1. You can have different choices depending on your particular use case, but let's say we initialize it to 1, and then we iterate what is called a message update rule until we converge. The message update rule takes all the messages that come into your node and multiply that by the local factor that you have. And if you want to calculate the message that goes, for example, from node 2 into node 3, you also multiply it by the tensor that connects 2 and 3. And that would be your message that goes from 2 to 3. You receive that message from 2 to 3, and then you continue to calculate the message, for example, from 3 to 4. You get the messages that are that you already know that are going in, and then you pass it forward until you calculate all the messages. So if you have a tree, you will get the exact answer. So you would, in a sense, this is equivalent to contracting this tensor network or factor graph. But if you don't have a tree, you will have a problem of convergence, and there is a separate question of how do you decide when you converged. So once you got the messages, once you either calculated everything if you have a tree, or you decided that you converged, you can calculate the marginal by just taking the messages that go into your node and applying the decision rule. So in the case of the usual belief propagation, where you calculate the marginals, you take the product of the messages that are incoming. So this is what is called sum product message passing. The belief propagation is applying a particular set of rules to the message passing. So in this case, we take the product of messages and do the sum over the local variable. Okay, and I can show actually that on an example that this algorithm will give you exact calculation if you have a simple chain. So let's start with, let's say we want to calculate the marginal probability for variable 1. And our conditional probabilities define the dependence between 5 and 4, 4 and 3, and so on. So the first message, first of all, messages are initiated to be ones. So the first message, we don't have any incoming messages into 5. So we would have to just take the edge tensor, sum it over the variable 5, and that would be our message from 5 to 4. Now we proceed to calculate message from 4 to 3. The message rule says that we have to take the product of all incoming messages and then multiply that by the edge tensor. So what we do is we take all the messages that come, for example, from 5 to 4. There are no other messages, and then we multiply it times the local tensor from 4 to 3 and do a summation over 4. We do the same thing for 3 to 2. We do the same thing for message from 2 to 1, and after all, we say that the probability of the marginal probability of 1 is sum over message from 2 to 1. And this is in fact the same as just contracting the full tensor network. If you expand the M5 to 4 definition, if you plug it in here, and then if you plug this thing here, you will end up in just doing the sum over 2, 3, 4, 5 over the product of tensors. So again, for the chain, it is exact. Now, what happens when we have a loop? If we have a loop, we will end up again going kind of in circles. And this particular example is interesting because we can understand exactly what happens. We can kind of analytically derive where will we converge and confirm that we will converge to the correct thing. And on top of that, we will give an intuition about what are what do these messages signify. It will be consistent with this notion of like what the message is telling you information about some side, like if you again here versus there. So the message tells an information to the receiver, hey, on my side there is this information. So let's consider this chain, right? Let's say all the tensors are exactly the same. We have a 4 variable tensor network. Let's say T1, 2, T2, 3, T4, 1, they're all exactly the same. And we initialize messages to ones, and now we start calculating the messages. So let's start with message from 1 to 4. We actually, sorry, so let's start with message from 4 to 3. We start with the messages that go into 4, and by the way, we have to start somewhere, so it's again it's kind of arbitrary where we start. But let's say we follow through from 4. So the first message is just 1. We don't consider that, and we multiply that by tensor t. Now this we assign to message from 4 to 3. Now we continue, and then we again multiply the message times the local edge that goes from 3 to 2. And again, we do the summation over both variables, over the variable that we are passing the message from. And then continue. So you see, we now accumulate t to the t, then t squared, then t cubed, and then t to the power 4. And this m0 just represents the what we initialized it. So it's a 1. So as we loop around, we get powers of t, which is our tensor, right? Like what does it tell us? What if we look at this tensor network and think about it from another perspective? Can we make a bridge to what exactly the tensor network is? And we can see that actually, if we look at this tensor network, remove the variable from it, and look at the tensor network that we get. So that would be the product of 4 tensors t, right? That have the open edge over here. And we want to represent this outside tensor network, which is t to the power of 4, as messages that come into the node 1. Those messages are independent tensors, so they are indexed by only index 1, one index. So essentially, we are trying to represent a tensor with 2 dimensions, or a matrix with a product of 2 vectors. So what is the best approximation to that? It is actually the best approximation to that would be just the highest eigenvectors multiplied together. And this is exactly what we will get if we do the multiplication of t to the power of something, right? As we multiply a matrix multiple times by itself, we arrive to the highest eigenvector. And turns out that the messages that we converge to are exactly the largest number eigenvectors. And in order to get the approximation, we just need to normalize by the eigenvalue. So this kind of proves again that your messages, the messages that come into the node are a close approximation of the environment that this node is connected to. Okay. Any questions so far? Okay. So let's go into examples. So here's an example of classical error correction. We have we want to encode some k bits of data in a larger code word, such that we are able to detect an error if the code word is somehow scrambled, or if the error occurs, and we want to correct that using a syndrome measurement. So once we get our code word or scrambled data, we can calculate what is the error and correct the error, getting back to the code word that corresponds to some data. So in a classical error correction, we take the parity check matrix H, and it maps from our code word into the syndrome. And notably that code words, all the code words map to 0, but the scrambled data and bit data, they don't map into 0, they map into syndrome. So the if you think about the parity check matrix, it has input space is your encoded information that can contain an error, and the output space is the space of syndromes. And once you got the syndrome, you want to understand what is the error correction that you want to apply. So you want to understand what is the error that corresponds to syndrome. That's error decoding. And now you can look at this parity check matrix and also represent it as a factor graph. And in this case, again, you have a bipartite graph where you have the data bits represented as circles, your syndrome bits represented as rectangles, and the H matrix tells us what are the connections between these. So for example, if we have an edge between data bit 3 and syndrome bit 2, we have a 1 over here. And different factor graphs, of course, correspond to different parity check matrices. But eventually, we can apply the same algorithm, the belief propagation algorithm, with a little bit modified message update rules. Those are more related to the generalized belief propagation, where you have edges that connect multiple nodes. So in the previous example I showed, we had edges that connect 2 nodes. We could have a more general case like here, where this rectangle connects 3 nodes, so that can be considered a hyperedge. Here we have the same situation. We initialize. So again, we want to solve the problem given some syndrome S, which is the values for the rectangles for the syndrome bits. We want to infer what is the most likely assignment to the data bits that we have. And from that, we would be able to infer what is the error. And from that, we can correct it. And we again, in the same fashion, we apply the belief propagation. So we initialize the messages with some particular rule that go from data to parity. And then we iterate parity. We alternate between applying parity to data message passing and then data to parity message passing. I won't go into details of why exactly we choose, but hopefully you can see the motivation between like what is this product sign doing here. We are taking the messages that come into this node, we apply some kind of summarization, and then we pass that message to we use that to calculate the message from this node to some other node. And we iterate that again, as in the previous example, we want to converge to some stable equilibrium. And we need to decide what is our stopping criterion. That is, something I won't talk about today, and it's an art in itself. And but if you decided that you stop, for example, when your messages don't change as much, that's perfectly valid criterion. If you found that you don't, okay, now my messages don't change much, I can stop the iteration and say use the messages to calculate the expected data bits, and then you can use that again to decode your error. So that actually is a very good way of decoding, especially for quantum codes. And in the quantum codes, what you usually do is you get these outputs from belief propagation, and then you need to apply an additional post-processing rule, which is called ordered statistic decoding. And so usually BP plus OSD is considered a very good decoding technique for quantum error correction. The reason why you need to do the decoding is that you can have a situation where your messages oscillate between different values. So you can have a situation like where you have a degenerate solution. So you have two or more solutions, and you need to decide which one do you choose. So that is where the decoding comes. So that's the first application, the error correction. Now, here is a different application. It's also pretty advanced, I would say. So let's say you have a quantum state. And let's start from this picture A. You have a quantum state that you represent as a tensor. And sure, you can represent your tensor as a dense tensor, so to speak. So you store every combination of the indices. In the same sense, your the probability distribution, as I mentioned earlier, for the student network, you can store it fully, and you can store a number for every combination of the inputs. But what you can also do is you can factor it out into these little pieces, and you can factor them out in different ways. You can factor them as chain, you can factor them as this grid, or some arbitrary graph, as a tree, or some arbitrary graph. Now, you having this representation of a state gives you the ability to preserve some notion of entanglement between different qubits in a quantum state. And this can allow you, it's like compressing the state into instead of having a large tensor, you compress it into a product of lower dimensional tensors. But if you want to simulate the evolution of this state, you want to be able to apply the quantum gates to corresponding qubits, such that you don't lose your approximation quality. And for that, you have to be in what is called the correct gauge. And that represents a particular, as a note, you can have different values. So for example, you can adjust the values of tensor T3 and at the same time adjust in an opposite way, adjust the values of tensor T2, and you can still have the same final value, right? So you have a freedom, more degrees of freedom than you actually need. And to find that representation that allows you to apply the gates without losing your approximation quality, you have to find this gauge. And the requirement for the gauge is that it's pretty interesting. After you absorb the diagonal tensors that are on the edge between you and another node. So this is a little bit jumping ahead, but you have a representation where you have a diagonal tensor that sits on the edge between two side tensors. So the gauge requirement is that after you absorb those tensors into the side node, you get a unitary tensor. So you can contract it with itself, conjugate it, and get an identity. This requirement actually is very similar to the message update rule. So you can use the message update rule to generate messages that satisfy this requirement. And once you got those messages, you can apply this gauging technique in between your gate application. And so these are some results from a paper by Flatiron Institute, by scientists at Flatiron Institute. And they demonstrate that they are able to reduce the time and increase the quality of solutions compared to some alternative gauging techniques. Okay, and then finally, another application of this is evaluating the tensor network that corresponds to circuit evolution, but in a different way. So before I was describing how to use belief propagation to converge the state into a particular configuration that you don't incur any errors once you apply the gates. But here, you can take a quantum circuit like this, and you can construct a tensor network from that quantum circuit in a more direct way. So your initial state would be represented as a product of one-dimensional tensors, and then you apply a gate. A single qubit gate would correspond to a tensor with two indices, or in this case, again, going back to our formulation, where you have variables and edges that correspond to, so edges correspond to tensors and circles correspond to variables. And you can apply this table essentially to each gate and build up a tensor network. And this graph would look like this if you apply certain simplifications. And then getting this graph allows you to contract the tensor network, and then in the end, you can get the final value of the circuit. So after you evolve, you want to calculate the probability amplitude for, let's say, state 111, right? You fix the output indices to ones, and you contract the tensor network that has all these intermediary indices. And this is essentially the same as, again, calculating the marginals given fixed some fixed condition. So tensor network contraction is the same, and we can use again this tool from classical probabilistic graphical models. Belief propagation can be used here, although here again it will give you an approximate value, and it will give you a better value if your graph is like a tree, or it will give you a worse value if you have a lot of loops. And again, you have the problem of finding the stop value. So that's the third application, and that's the end of my presentation. We have roughly 10 minutes for questions.
For the insightful talk, let's see if anyone has some questions. Yes, go ahead.
Yeah, so You talked about tensor network based simulation for quantum circuits. Is it able to kind of uh, uh, compete with any of the experiments for showing quantum advantage, like the random circuit sampling problems?
Well, that's a whole, that's a question for another lecture for sure.
Okay.
For the short answer is yes, and this is the prime adversarial that the quantum advantage claims are fighting against. They construct, in fact, the Google supremacy experiment back in 2019. The circuit was constructed particularly in a way so that you can't easily simulate it with a tensor network approach, because it's pretty clear that you cannot simulate it with a state vector approach. But in order to disable the tensor network approach, they had to apply this fsim gate, which is more complicated to simulate than C0, for example, on tensor network, because C0 has a diagonal part, and fsim gate is harder to represent as a diagonal tensor. So yeah, and tensor network methods are also evolving all the time, and things that were previously not considered possible are very much possible now, which is what happened with 2019 experiment. Yeah.
Any other questions? Oh, if not, maybe I can ask one first. So I'm really curious. So then I think people start introducing belief propagation to error correction. It's a very recent thing, right? It's like just a couple of years ago.
Yeah.
So how did people use it before? Like, where did you first learn about this? Like, I'm just kind of curious. Because it seems like it has deep connection with like generalized like icing model physics and this kind of things. So I'm just trying to understand, eager to learn.
Yeah, absolutely. Actually, belief propagation. So the paper that I was using here for the images, it is a 2012 paper. I should have put some information about that. Oh, it's actually 2003. This one. Yeah.
Oh, okay.
And is this paywalled? There is probably an archive version. Oh, actually, here it is. And one of the applications, actually, by the way, if you're interested in this is a very good introduction. It starts with a pretty basic examples, and it builds up nicely, connecting the physics part. And here, another example for the error decoding. And this is one of well-known applications of propagation. So this is not recent. What is recent, I think, is applying that to quantum error correction and applying that in combination with this post-processing step. This is where you get good results, because belief propagation, I'm not an expert in this. I'm just kind of starting to learn the error correction, but I think in a classical, belief propagation is not the best way to go with classical error decoding. But for quantum, apparently, it's pretty good if combined with this post-processing. Yeah.
Yeah. Thanks for this resource. I think we can share with the student. And so maybe one follow-up question is because for different error correction codes, so at least from the lecture, what I see is, so what you need for belief propagation to work for quantum error correction seems very general. You just need the edge matrix. So, but if you look at the what people do is like surface code, they treat it as a graph problem. So they have this like weighted graph matching decoder, and for color codes, I think it's usually not modeled as a graph problem. So people have a different design of decoders. So can you comment a little bit on that? Like for different error correction codes, like is belief propagation like kind of very general technique applied to any codes, or is that like you know, for very suitable for certain codes?
Yeah, that's a great question. I think you can apply it to anything because from the formulation, you can create a factor graph from any decoding matrix, right? Like so. Whether it works or not, that will depend on the matrix. But from the practice, as I understand, the belief propagation is mostly applied to CSS codes and in particular to the QLDPC. These are this is the paper that I studied for this particular application, and yeah, so these are the codes that are known to be I think general in a sense that they allow you to they allow you to construct codes that are correcting like whatever you want, and they are like very good because you can easily implement them on hardware. Yeah.
Okay. Okay. Yeah. Thanks. Yeah. I think this is the paper I know when people, at least in the field of quantum error correction, start looking at belief propagation.
Yeah.
I haven't taken a detailed look, but yeah, I can. Sounds like a good resource.
Yeah. So what I was talking about is like the screenshots are from this from the supplementary, and again, you know, you put the messages from parity to data, from data to parity, and then iterate until you converge.
Yeah. Cool. Yeah. Let's say if we have more questions or general questions.
You mentioned about quantum computing in internship.
Yeah.
Could you tell us more about the internship opportunity that you were talking about?
It's an internship in the quantum in the math libraries group. I will have to double check if it's still open because on LinkedIn I just looked, it was closed. So you would have to go to something like this, and we can check if it's still open on the board. But if it's closed, then it's closed. Yeah. So you can see. Yeah. And see entrance here. So it could be closed. Yeah. So this is like very recent update. So could be put back still. So keep an eye.
Oh, thanks.
And maybe a quick follow-up question on that is, do you know a little bit about what they're looking for? Like what kind of project like they're mostly interested, or like what kind of skills they would like to see people have?
Well, I guess the perfect candidate would have some publications and track record of programming skills. So it will show that you understand both the quantum part and you are also able to write good code. And I mean, I guess, yeah, that's pretty much it. So some projects connected to quantum, you know, if it's not a publication, it could be a contribution to some repositories, to some open source. Yeah. But usually it's written on a job description. It's probably the best thing to consult.
Okay. All right. Let's see if we have some final questions. It's already time. If not, let's thank the speaker again. Yeah. So thanks, Dan. So I think I can follow up with you about posting videos online, and yeah, if you're okay with that, we'll update the YouTube channel.
Sounds good.
Sounds good.
Thank you.
Yeah, thank you. Have a good night.
Thanks. Bye.